What if the specs on your PC box, the numbers you researched, compared, and ultimately trusted, were never real measurements at all? Not approximations, not simplified figures, literally made-up marketing labels that haven't corresponded to physical reality for decades. And here is what makes this genuinely strange. The engineers who designed these chips know this. The journalists who cover launches know this. And yet every product cycle, the numbers get smaller, the marketing gets louder, and almost nobody says it plainly. By the end of this video, you will understand why the hardware industry has been running on a kind of shared fiction. And more importantly, how that fiction shapes every single buying decision you make. Let's start with the most fundamental number on any chip box. The nanometer label. 3 nanometers, 5 nanometers, 7 nanometers. These are the kinds of figures that dominate chip announcements, and they sound like precision measurements. Atomic scale engineering, hard science. And for a brief period in the history of computing, they actually were. In the early decades of semiconductor manufacturing, the node number genuinely corresponded to a physical dimension on the chip. Specifically, the gate length of a transistor. If a chip was labeled 65 nanometers, something on that chip was actually 65 nanometers. That relationship ended in the late 1990s. According to semiconductor industry records and analyses published by outlets like EEJournal, since at least 1997, process node names have been assigned purely on a marketing basis. No dimension on the circuit, not the gate length, not the metal pitch, not the gate pitch, actually matches the number on the label. A chip marketed as 5 nanometers may have no single feature that is physically 5 nanometers. As one analysis put it bluntly, nothing about a 5 nanometer process has any real relationship to 5 actual nanometers. The label is a generational branding term. It means newer than the last one. That's it. The reason this persists is competitive pressure. Once one manufacturer started naming nodes aggressively, using smaller numbers to signal advancement, even without a corresponding physical breakthrough, everyone else had to follow. If your competitor calls their chip 5 nanometers, you can't call yours 7 and expect customers to understand the nuance. The marketing logic becomes self-reinforcing and the numbers detach further from reality with each generation. Now, this might sound like a minor technicality. A label is a label. But here is where it starts to matter in ways most people haven't considered. If the most fundamental spec, the one that defines the entire chip generation, is a marketing construct, what does that tell us about how the rest of the specs are presented? Because the nanometer problem is just the beginning. Take Moore's law. Nearly everyone who has spent time in tech circles has heard it cited as a fundamental rule. Computing power doubles every 18 months. It's treated as a law of nature, like gravity. Hardware journalists invoke it. Executives use it to justify roadmaps. Gamers use it to decide when to upgrade. The 18-month figure was never said by Gordon Moore. Not once. Moore's original 1965 prediction, based, by the way, on exactly 5 data points, was a doubling every 12 months. He revised that in 1975 to roughly every 2 years. The 18-month number came from an Intel executive named Dave House, who was talking about overall computing performance, a composite of transistor density and transistor speed, and explicitly stated it as his own projection of a different metric. In a Stanford interview, Moore himself addressed this directly. He said, and I am quoting here, "I never said 18 months. That's the way it often gets quoted. The misattribution became so embedded in the industry's vocabulary that it took on the authority of the original without anyone checking the source. This matters because Moore's law, the real revised version, is already effectively over for the purposes it was originally describing. Transistors are still getting smaller in some sense, but the performance and efficiency gains that the law implied have stopped scaling the way they once did. And the reason for that collapse is the next piece of this story. Here is something almost no marketing material will tell you about the chip running your PC right now. It cannot turn all of its transistors on at the same time. This is not a bug. It is not a design flaw in your specific unit. It is a fundamental and worsening property of every modern processor. The phenomenon has a name researchers use: dark silicon. And it describes the fraction of a chip's surface area that must remain powered off at any given moment. Not because it's broken, but simply because if everything fired simultaneously, the heat generated would destroy the chip. The underlying cause traces back to a principle called Dennard scaling, named after Robert Dennard of IBM, who who observed in 1974 that as transistors shrank, their power density stayed roughly constant. Smaller transistors, same power per area. This was the hidden engine behind decades of progress. You could pack more transistors in without proportionally increasing heat, but Dennard scaling broke down around 2004 to 2006. Transistors kept shrinking, but power density stopped scaling with them. The result: every new generation of chip is denser, but not proportionally more efficient. An increasing fraction of that denser chip must stay idle to keep the whole thing within safe thermal limits. Research published in academic journals has framed this as an exponentially worsening problem with each process generation. Some projections suggest that as chips continue to scale, the proportion of silicon that must remain dark could become the dominant design constraint. You're not buying a chip that runs at full capacity. You are buying a chip that is carefully managing which parts of itself are allowed to wake up at any given moment. The dark silicon problem is also why clock speeds stopped climbing. This is a fact that many PC enthusiasts know abstractly but rarely connect to its actual cause. Clock speeds plateaued around 3 to 4 GHz sometime in the mid-2000s, and they have barely moved since. The common assumption is that this reflects some engineering plateau, some practical limit where faster just wasn't worth it. What actually happened is more specific. In 2004, Intel canceled an in-development 4 GHz CPU. The cancellation wasn't about viability in the long run, it was about heat. The power density required to run that chip at that frequency generated heat that was unmanageable with conventional cooling at the time. Without Dennard scaling to keep power density in check, pushing frequency higher became a thermal problem faster than an engineering one. The industry's response was to stop chasing frequency entirely and pivot to adding more processor cores instead. This pivot, from faster single cores to more cores running in parallel, completely reshaped what software has to do to get faster. A program that isn't written to use multiple cores simultaneously gets essentially no benefit from a 12-core chip versus a 4-core chip. The hardware evolution forced a software evolution that is still playing out. All of that traces back to one canceled chip in 2004 and the collapse of a scaling law most people have never heard of. Now, here is where the hardware mythology becomes genuinely personal. The chip inside your computer is almost certainly partially broken. Not in a way that causes crashes or errors, in a way that was quietly accounted for before it ever left the factory. Every processor starts as a die cut from a silicon wafer. Manufacturing at the scale of billions of transistors means imperfections are statistically unavoidable. A contaminated area here, a failed connection there. Rather than discard these chips, manufacturers use a process called binning. Each die is tested after fabrication. Functional blocks and cores that have defects are identified and disabled. The chip is then sold at a tier that reflects what remains intact. An i9 with 2 defective cores becomes an i7. A graphics processor with a broken shader cluster becomes a lower-end card. But binning goes further than defect management. As TechSpot and other hardware analysts have documented, manufacturers sometimes disable fully functional cores on otherwise perfect chips purely to maintain market segmentation. If factory yields are high and nearly all chips come out perfect, you'd end up with too many high-tier chips and not enough mid-range ones to meet demand. The solution: take a fully functional die, disable 2 cores, in firmware or physically, and sell it as the mid-range product. Some portion of the processors marketed as mid-range are physically full chips with artificial restrictions applied at the factory. This is not speculation. It's a known and documented practice in the industry. The technical term used internally is harvesting. The commercial term is product segmentation. The chip you have may be more capable than the label suggests. It has simply been capped to fill a market slot. And speaking of caps and marketing gaps, let's talk about a few specific upgrade decisions that the hardware industry has a financial interest in presenting as more impactful than they actually are. The jump from PC 3.0 to PCI 4.0. The interface that connects your graphics card to your motherboard is frequently marketed as a meaningful performance upgrade. Double the bandwidth, faster data transfer, next generation readiness. And on paper, the numbers support that framing. In practice, benchmarks across numerous game titles consistently show an average difference of 1 to 4% in frames per second when a high-end GPU runs at 16 lanes on PC 3 versus PCI 4, that is within or barely outside margin of error for most use cases. The reason the gap is so small is fundamental to how gaming hardware actually works. Modern GPU memory holds all active game assets locally on the card itself. The PCIe bus connecting the card to the motherboard mostly carries low-volume command traffic. Instructions, not bulk data. There isn't enough data flowing across that link to saturate even the older standard in typical gaming workloads. The exception, and it is a real one, is budget graphics cards configured with fewer lanes, where PCIe narrower bandwidth does create a genuine bottleneck. But for the mid-range and high-end cards that most people buy when they are thinking about PC generation, the upgrade is largely invisible in practice. The NVMe versus SATA solid-state drive comparison follows a similar pattern. NVE drives of the latest generation advertise sequential read speeds around 7,000 megabytes per second. SATA solid-state drives cap at roughly 550. On paper, that is a 12 times difference, the kind of gap that sounds transformative. Load time benchmarks across games show differences of 1 to 2 seconds per level load, sometimes less. The reason is that games don't read data the way sequential speed tests measure it. Game engines issue thousands of small random read requests, loading a character model here, a texture there, a physics asset somewhere else, not large sequential streams. At low queue depths with small file sizes, NVE and SATA drives perform far more similarly than their headline numbers suggest. As hardware analysis sites have noted, the actual bottleneck in most game loading scenarios is the game engine itself. The time spent processing and decompressing assets after the data arrives, not the storage interface delivering it. Where raw NVMe bandwidth will genuinely matter is in next-generation engine features like direct storage, which is designed to bypass traditional CPU processing bottlenecks and stream directly from storage to GPU memory. That's a real technical development. But for the library of games that exists right now, the 12 times speed difference on the box translates to seconds of real-world impact, if that. There is a pattern running through all of this that's worth naming directly. The hardware industry, like most industries, has a structural incentive to present its specifications as more meaningful, more transformative, and more legible than they are. Nanometer labels are marketing constructs. The most cited version of Moore's law was never said by Moore. Your chip cannot use all of itself at once. The processor you have may be artificially restricted, and some of the upgrades that feel most compelling in spec sheets deliver the narrowest real-world gains. None of this means the engineering is genuinely remarkable. The fact that we are manufacturing chips with features measured in the single-digit nanometers, even if the label doesn't map to a real ruler, is an extraordinary achievement. The pivot to multi-core design after the frequency wall actually produced a different kind of progress. The hardware is impressive. The marketing language wrapped around it is something else entirely. Understanding the gap between those two things doesn't make you cynical about technology. It makes you a more accurate reader of it. You stop optimizing for spec sheet numbers and start asking what actually changes in the workload you run. And more often than not, that question leads to a different answer than the product page suggests. If this kind of gap between how technology is presented and how it actually works is something you find worth understanding, this channel is built around exactly that. The documented, sourced, less told side of the hardware and gaming industry. Not conspiracy, not hype in the other direction. Just a more honest accounting of what's actually going on inside the machines most of us use every day.